Good day to everyone, especially to our dear panelists. Good day. Good day to the viewers. Hello, good morning, good day. And my name is Marvidi Gusar, and I'm here to present my research study entitled 3D Diagonals, Computing for the Number of Diagonals of a Solid Figure. So, geometry introduced the concept of diagonals today as essential for understanding both 2D and three-dimensional spaces. The idea of diagonal in 2D is more likely straightforward and only face diagonal. So the researcher explored its extension to the 3D figure shapes that leads to exploring more on the concept about the total number of the diagonals in the dimension figures be figures given solid figures like that. So those solid figures are cube, pyramid, pentagonal prism, and can also be cylinder and such. So in exploring more on making things simple and finding how many diagonals are there in a 3D figure. So the study leads to the clear presentation on how a 3D figure or 3D dimensional figure be calculated of the total number of diagonals. So according to Fujita 2014, the 3D diagonals are not only fundamental in mathematics but also in education. It holds significant value in education and a real-life application. So according to Jawad and Ledwith 2021, so the knowledge is particularly important in fields such as engineering, architecture, and design, where the ability of analyzing 3D dimensional structure is critical. So the engineering and the architectures are rely on diagonal measurement to ensure precision and stability in construction projects. So the example of this is the scaffolding used in building house, the 3D floor house or 3D a 3 three-floored house, a three-floored room or apartment and such. It can also use in strongholds for hanging bridges, and in architecture can be easy to design or the outer layer that can make the building strong or such. So the methodology, let's proceed to the methodology. So exploratory research is an investigative method used in the early stage of a research project to delve into the topic when little to no existing knowledge or information is available. It is a dynamic and flexible approach aimed at gaining insights, uncovering trends, and generating initial hypotheses, according to Apinio Research 2013. So, as a result and discussion, this section shows below are the following. Uh, the distinctive formula in getting 3D diagonals that shows clear relationship between vertices and the edges to obtain the total number of both face diagonal and the space diagonal in the solid figure. So the process of evaluating the 3D diagonal formula. So the problem asks for distinctive formula to which we can know the exact number of diagonals in a given 3D dimensional figure. Therefore, the following conjecture were formulated. So, how can we solve easily the total number of diagonals as same as the total number of the whole total number of the face diagonal and the space diagonal within the 3D dimension figure. So, the given following formula revision, which is V times V minus 1, is the number of the way you can connect a certain vertex to another vertex, while we divide it to 2 to show that the two vertex shows a pair. Then we subtract it with the number of edge to remove the excess pair, which signifies the only remaining pairs are diagonal. So wherein V in the formula is vertex and the E in a given figure is the edge. So to prove the conjecture, to verify the conjecture, let's use the illustration of a solid figure using the formula, which is V, the quantity V minus 1 divide 2 minus E, wherein V is the vertex, as we said earlier, and E is the edge. So the given illustration is the solid figure is a cube. So in here, up in my upper presentation, so the V there is 8. Vertex A, vertex B, vertex C, D, E, F, G, and H. While the edge there is A to E, A to C, C to D, D to B, A to B, and those other sides. So from this formula, to verify the conjecture that it can solve the total number of the diagonals in a solid figure, here is the illustrative example. So this is a cube with that has 8 vertex and 12 edges. So V is 8 times 8 minus 1 over 2 minus E, which is the E there is 12. So we solve this. So 8 times 9 divide 2 minus 12, where 8 times 7 rather, 7 is 56, divide 2 minus 12 is equal to 28 minus 12, and the answer there is 16, which is, we can see in the next illustration there, that 16 diagonals. So there is 16 diagonals inside and in the face diagonal, the total of face diagonal and the space diagonal inside the cube. So let's try to prove it using the illustration. So here above, there is here is the cube, which this is labeled as A. This is labeled as B, C, C and D. And this is labeled as E, F, G, H. So the face diagonal the face diagonal there is this one to this one, which is line segment AD. Line segment AD, line segment CH. Mali yung aking label. Dito ay C pala. Dito ay CH. Mali. Line segment CH, which is here to there. Itong nasa likod po. So, line segment AG. Itong nasa unahan. Line segment BC. Line segment FD. Line segment DG. Itong nasa unahan. Yan po ang face diagonal, yung nakatapat sa labas. DG, line segment EB, line segment AF, line segment BH, line segment FG, line segment EC, and line segment EH with a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 face diagonals, and these face diagonals are, and the space diagonal, burahin po natin aring nasa face para hindi magulo. The face diagonal there is, here is B pa rin, C to G, line segment C to G, line segment D to E, line segment BF here to there, and the line segment A to H. So, in total of 4, which is 4 plus 12 is 16 diagonals. There is 16 diagonals in one solid figure called cube. So, let's have another example, which is the square pyramid that has 5 vertex and 8 edges. So, using the formula V minus 1 all over 2 minus the edge is equal to 5 times 5 minus 1 over 2 minus 8, where 5 times 4 over 2 minus 8. When 5 times 4 is 20, divide 2 minus 8. And 20 divide 2 is 10 minus 8. So there is 2 diagonals in a square pyramid. So let's prove it in the illustration in the next slide. So there is only have face diagonal. So those are line segment BD and the line segment CE. So it proves that this 2 is the 2 diagonal of the square pyramid. So how about the solid figure cylinder? Cylinder. So cylinder have no vertex and also don't have a edges. So let's apply it. Let's see if there is a diagonals inside uh, the cylinder. So V is 0. So 0 times 0 minus 1 all over 2 minus 0 is equal to 0 times negative 1. Since 0 minus 1 is negative 1, divide 2 minus 0. So 0 times negative 1 is 0. Divide 2 minus 0, which 0 minus 0 divide 2 is 0 minus 0. So the answer here is 0. Since there is no vertex and edges in cylinder, there is don't have a diagonal. Since the following example illustration is cube, cylinder, and square pyramid, let's try it in a prism, a pentagonal prism. So, the pentagonal prism has a vertex of 10 and also have the edge in total of 15. So let's try it. Let's see how many diagonals there in pentagonal prism. So let's use the formula V minus 1 over 2 minus the edge. So vertex times vertex minus 1 divide 2 minus 15, where 10 minus 1 is 9. Divide 2 minus 15. So 10 times 9 is 90. So 90 divide 2 minus 15, where 90 divide 2 is 45 minus 15 is equal to 30. So there is 30 diagonal in a pentagonal prism. So let's check if it is correct. So in a face diagonal, as you can see in the next illustration, the face diagonal there, are the face diagonal there is line segment AD, line segment AC, line segment CE, line segment BD, line segment FI, line segment BE, line segment GJ, line segment FH, line segment JH, line segment IG, line segment AG, and line segment FB, line segment BH, line segment CG, line segment DH, line segment CI, line segment JD, line segment DI, line segment AJ, line segment EF, with a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 face diagonal, and the space diagonal are line segment AH, line segment AI, line segment BI, line segment BJ, line segment CF, line segment CJ, line segment DG, line segment DF, line segment EG, and the last one, line segment EH, in a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. So 10 plus 12 is equal to 30 diagonals. So the easiest way to get the diagonals of pentagonal prism is to use this solution with a given value of vertex and edge, so that you will not have a difficulty in writing this many diagonals to identify how many are there in this prism or this figure or in the diagonal. As a conclusion and recommendation, the discovery of formula in getting the three-dimensional diagonal in a figure plays a significant role not just in the geometry but other fields like engineering, architects, and design. To get simply the exact diagonals of a given 3D figure, in this study, the relationship of vertices and edges serves as a guide in discovering the formula for exact number of diagonals in a solid figure, covering, or it includes the total number of the face diagonal and the space diagonal of a figure, letting out the example to prove the conjecture, and turns in the end as valid, thus making the formula finding the number of diagonals in a 3D figure is true. As a basis of knowing the exact number of diagonals, the researcher recommends in using the formula for looking at different perspectives regarding 3D figure of what they can observe more from it. Moreover, making more observation about the relationship between the characteristic of 3D figures and have a different result aside from the currently known discovery. That's all of my presentation. Good day again, and thank you for watching.